Bismillah ar-Rahman ar-Rahim. So, last time we have looked at the single effect evaporation system. This is, or that was the start of considering the systems of large production of desalinated water. Remember that the example that we have taken last time was considering a system that can produce 1 kilogram per second. If you are considering 1 kilogram per second, this is huge. I mean, you just multiply that into 3,000, it's 3,600 kilograms per hour into 24. We're talking about something like 86,400 kilograms per day. So that's the start of substantially bigger size units. And this is basically what we're going to consider in this set of lectures for these few weeks that are going to come, that these are the conventional systems that are responsible for producing considerable amount of desalinated water per day. For example, the units that are but I'm not talking about a single effect. I'm talking about the units that are producing that basically the multi-effect desalination units that are in Marafiq. They have units that are producing 805,000 cubic meters of water per day, which are made of several units, something like close to 27 to 30 units. I'm not sure about the number. Each one is producing something like 30,000 per day. So we're talking about some substantial amount of desalinated water which is being produced. These units are basically huge in size, and definitely they would require steam. So we're talking about, again, a substantial amount of energy which is needed to run these units. The units, however, are stable, they are reliable, and they are the units that can work at least for 25 years, I'm sorry. And as I just probably mentioned before, the multi-stage flash desalination systems that were designed to live for 25 years here, they have exceeded about 37 or 38 years of operation with a plant factor of 95%. Plant factor, it means that the unit is operating 24/7 for the whole year, and it's down only for 5% the number of days of the year for different types of maintenance that would be required here and there. So again, it's a units which are reliable and operating for a long time and stable. So you can rely on it for producing amount of water. I've just seen like a tweet that has been published yesterday by the SWCC, Saline Water Conversion Corporation. And they are talking about they are able to produce amount of desalinated water, which is enough to provide 3 cups of sweet water for every single person in the whole world. This is just, I mean, they are talking about how much they are producing and how does this compare with an existing population. So going back to this, I mean, and we have seen also the drawback or the disadvantages of these systems, and these disadvantages or the disadvantages include we are rejecting brine at saturation temperature of more than 70 degrees centigrade. There is seawater after being heated to high temperature of about 70 or close to 70, it's been rejected to the atmosphere. So we are rejecting substantial amount of energy to the atmosphere as well. And that's why the single effect evaporation with a performance ratio of about slightly less than 1 is not attractive to operate. And that's why we are considering basically the issue or the configuration to be modified to multi-effect desalination system. But before we get into the multi-effect desalination system, let's have a look on modifications done to this unit. I talked about this last time, so talking about the vapor compression or the idea of vapor compression being added to these units. And by the vapor compression, we have basically four subcategories of that. Thermal vapor compression, this is what we are going to talk about today. There's mechanical vapor compression, absorption vapor compression, and adsorption vapor compression. The first two are going to talk about in details. The second two, I might just provide it as some sort of a reading assignment. I might just provide you with one or two papers of that we have produced in this area, just to read it and get an idea of this kind of units. So it's the thermal vapor compression that we are going to consider today, and this is the layout. The idea is simple and beautiful, actually, because we could simply reduce the amount of steam that we are getting from the power plant significantly. I'll just go through the description again. What we see here is the condenser, or we call it the feed preheater. Seawater enters here to the condenser, where it will be heated from the seawater temperature, T cooling water, up to a temperature of TF, feed temperature. And then we are going to take the feed quantity alone, m dot feed, that is going to be sprayed in the evaporator, and the rest, which is m dot cooling water, will be thrown away. So that is basically essentially, and this is again, that remains one of the drawbacks of this system. Again, it's still a single effect evaporation unit. The feed is going to be sprayed here over tubes that have steam passing in. The steam is going to condense, giving off its latent heat that will heat that feed into the saturation temperature. Part of it will evaporate and rise up, whereas the rest is going to be collected at the bottom as brine, and then we are going to reject it, which is again rejected as the saturation temperature of the brine, TB. The vapor which is generated at a temperature TV, and remember TV is less than TB by boiling point elevation. The vapor is going to be leaving the unit here, and it will be splitted. Part of it is going to go to the condenser, m dot condense, and the rest is going to be entrained due to the low pressure at the throat of the thermo vapor compressor. The thermovapor compressor is going to receive motive steam, m dot motive, at a temperature and pressure of motive steam. This is what you get from the power plant, which is slightly high, by the way, slightly compared to the steam that could have entered here into the evaporator right away. That steam here is going to compress in the nozzle. Its velocity will increase, its pressure will decrease until it reaches sonic velocity. Sometimes this unit is having a conversion diversion nozzle inside, so that you can reach supersonic speed as well, which means that it's extremely low in pressure. That creates the low pressure that sucks some of the vapor upward. And then there will be a throat where this motive steam and the entrained vapor are going to mix together. And after that, a diffuser where reduction of velocity and increase in pressure is going to occur until it leaves with a pressure PS, and the saturation temperature is going to be the saturation temperature corresponding to PS. This is the one which is going to enter here. So we have used steam, yes, but part of this steam is our own generation. We have generated it within the unit, and we are getting less quantity from the power plant and or from the boiler, and this is one benefit. Number two benefit is that the amount of steam that will go to the condenser is less. which means that we are going to use a condenser of less surface area. And that's another benefit, that you have downsized the compressor. And because the compressor is small and the quantity of vapor which is coming here is small, then the amount of water that you are going to bring in for to make sure all the vapor will condense is going to be less. So we're having less m dot cooling water per distillate and less smaller pump, which is going to take the seawater and pump it in here. So it means that the benefits that we are going from, that we are going to gain from this addition of the TVC, the thermal vapor compression unit, or what we sometimes refer to as the ejector, are several. We reduce the quantity of steam which is coming here. We reduce the size of the condenser. We reduce the quantity of seawater that we are going to bring from the sea. Accordingly, we have reduced the pump size, which is going to pump the water. Reducing the pump means reducing the capital cost. So a capital cost reduction here, another capital cost reduction on the size here, and the running cost of, which is the power of the pump to circulate less quantity or less flow rate of the seawater, is going to be less. So these are all benefits. The components that we have are the evaporator, the steam ejector, and the feed preheater or the condenser. And the first one and the third one are the ones that we talked about in details last time.
Excuse me,
So
doctor.
yes,
I, doctor, want to ask what's going to be the m dot distillate then? It's going to increase or decrease since we are actually decreasing the m dot vapor and we are also taking the entrained vapor. So what's going to be the impact on the desalinated water?
it's not affected. I mean, we are doing the analysis here, assuming that we are having 1 kilogram per second production. Note that if the quantity of the vapor which is coming here is 1 kilogram per second, and it has been splitted here. So, for example, zero point 0.8 kilogram per second is going to go to the condenser, and zero point 0.2 is going to go to the TVC. The zero point 0.2 that has gone to the TVC has been mixed with a certain amount of steam here, isn't it? And then this mixture is going to go to condense in the condenser. We are going to retain back this zero point 0.2 here. And whatever we got from the power plant will return to the power plant. So the zero point 0.8 is going to add to the zero point 0.2, and we are going to have the 1 kilogram per second again. So the productivity of the unit has not been affected. What has happened here is that we have less steam, and accordingly, when I'm looking for the PR, the performance ratio, as m dot distillate over m dot steam, that m dot distillate has not been reduced. It's the same quantity, but the steam quantity has reduced, and hence the PR has increased.
Okay, doctor. Thank you.
Right? Or you can put that, you can look at it the other way. You can say that I'm going to get the same steam that I used to bring from the previously, and then I'm going to add to it in this quantity. Then you are going to get more than 1 kilogram per second of the distillate. So you can do it different ways. What we did, we fixed m dot distillate, and we found that m dot steam should be less. We could have done the opposite. We could have fixed the quantity of steam that we are getting, but you'll find that m dot distillate is going to increase, because you have basically increased the quantity of steam that has entered here, as if you have increased the Q evaporator. So it's going to evaporate more vapor from here, and then you are going to get that. So you can look at it from both angles, either from the angle of fixing productivity and finding out that the Q that we have is going to be less, or vice versa. Fix the steam, you'll find that you are going to get more distillate water. So I've seen the evaporator. I've gone through it last time. I've looked even the classification of evaporators and different types. Currently, the one which is used is the tube with horizontal bundle of tubes in evaporator, which is made up of tube bundle or the heat exchanger, a place for the vapor to rise, a distribution sprayers to spray the water, a mist eliminator to make sure that droplets carried out by the vapor are going to be retained back again to the brine pool, and so on. And the condenser is nothing but a shell and tube heat exchanger. Then the ejector or the thermovapor compressor is made up of a steam nozzle. Normally, or usually it's like a conversion diversion nozzle. There is a suction chamber. This is where the low pressure is created. There's a mixing zone. It's a throat where we mix the motive and the entrained vapor together, and a diffuser where the decrease in velocity and increase of pressure is occurring. Now, this is basically a typical sketch of a section inside one of these ejectors. The motive steam here is coming from left to right. So whatever we are getting from the power plant is entering here. M dot motive, motive steam pressure, and motive steam temperature. This is what is coming here. This is taken from, for example, the low pressure or the medium pressure turbine. It is entering into a convergent divergent nozzle. At the throat of the nozzle, we are reaching sonic speed. As we are moving here, there's a nozzle, so the pressure reduces. The pressure keeps on reducing and the velocity keeps on increasing. You can see that velocity is going up and pressure is going down. And then it's a convergent divergent nozzle. So after P1, the reduction in pressure continues because you are here achieving supersonic velocity of the steam, and it is going at very high speed, more than, definitely it's supersonic, so it's higher the speed of sound, until it reaches here with extremely low pressure. This is the suction chamber. So this whole chamber is supposed to be at very low pressure, and that creates the entrainment of the vapor here. So the vapor which is leaving the evaporator somewhere is going here, and part of it, due to the low pressure, is going to be entrained here. As it being entrained here, it is going to be mixed with the motive steam here. So the throat here is our mixing chamber. And this is where the pressure stabilizes a little bit. And then we are going to have sort of a shock wave. The velocity reduces, the pressure increases a little bit. And this is actually consequences of mixing at this very high speed. After this, it's going to go through the throat, where velocity is keep on reducing, pressure is going to increase up to a value of PS. PS definitely is higher than the pressure of the entrained vapor, which is the low pressure here. But PS is less than the motive steam pressure. But you are compressing the entrained vapor. You have basically expanded this PM, the motive steam, to very low pressure. You mixed it with a low pressure entrained vapor, and then you are compressing them again to PS, which is an intermediate pressure in between them. And this is the pressure which is going to be admitted to the evaporator for heating as a source of steam heating. The characteristics that are um, associated with the use of the TVC would basically include what we refer to as the entrainment ratio, RA, and what we call the compression ratio. Compression ratio basically is PS divided by P, entrained vapor, and the value here is in the order roughly of, say, 2.5 or so. The RA is basically the M dot motive steam divided by M dot entrained vapor. These two characteristics of the ejector are having a certain practical range for them to operate in. And you should operate it in what they call a critical condition. So a condition that would guarantee that this unit is going to operate and operate steadily and deliver the required quantity of steam per unit time at the required pressure and temperature. The third component is the condenser, and we have seen the condenser already. It's a condenser, and sometimes they call it feed preheater because it does preheat the feed, the seawater from tea cooling water to tea feed, which is close to the saturation temperature. So the requirements in terms of additional energy, external energy is less. And this is basically the kind of energy or heat recovery that we have for the unit. The feed water is chemically treated, which means we are talking about anti-scalant, anti-foaming, and anti-fouling components or chemicals are adding to the water. It's like a dose that should be given to the water before it is admitted to the evaporator. And usually, the vapor temperature is less than the boiling or the saturation temperature, the brine saturation temperature by the boiling point elevation. We have a demister, and the demister has a function of uh, forbidding the entrained vapor to move up. If we have in the system, if we have like sprayers and there is vapor rising, it might happen that the vapor on its way up, it can carry some of the tiny droplets, especially the sprayers are breaking the seawater into small droplets. Some of these droplets can be carried by the vapor, so that's why you have a mist eliminator. It's like a net, like a filter, so that you filter out all the water droplets and you only allow the vapor to pass in. The ejector increases the pressure of the entrained vapor, which is m dot entrained vapor. You heat, you compress that from a pressure of P entrained vapor to P steam. The pressure energy of the motive steam to generate the vacuum and compress the entrained vapor to the required pressure. The motive steam expands in the nozzle where its pressure reduces, its velocity decreases, and just high kinetic energy is there. Here I'm just repeating again the description of what's happening with the ejector. The conversion diversion nozzle results in supersonic speed, which means that we are talking about reducing the pressure down, and that would be the value of the entrained vapor. So this vapor is going to be entrained to be mixed with the motive steam. Both of them, upon mixing, pass through a Venturi diffuser so that the velocity would decrease and the pressure would increase, reaching to PS, which is the delivery pressure of steam leaving the ejector. And here are the kind of, for the operation, uh, we try to keep some typical values for best operation of the unit, like stable operation of the ejector, the critical pressure ratio of the suction pressure that would equal or exceed 1.81 for the water vapor, definitely. The suction pressure would be like 0.55 or less of the discharge pressure. And the entrainment ratio by definition is m dot motive steam divided by m dot entrained vapor.
By critical pressure ratio mean it mean compression ratio.
Yes, I said it's a typical value we use as 2.5. Anyway, this value should be more than 1.18. Sorry, 1.81. Now what we'll be left with is going through the analysis of this system. What you see here is not new, because when we are talking about seawater that's going to enter into the evaporator, if this is the evaporator here, then the seawater that enters is basically m dot feed. This m dot feed will be divided into m dot vapor and or m dot distillate, both are the same, and m dot brine. So this equation is, we have written this equation. Note this equation is going to remain with us For the rest of the single effect, the multi-effect, the single stage, and the multi-stage flash. So we're going to keep on with this. If you are going to go back and refer to the book, which is there in the blackboard, you'll find that going through chapters 2, 3, 4, 5, 6, this equation will always be there. 2 is what we covered last time, the single effect evaporation. 3 is what we are working on now, which is the single effect evaporation with vapor compression. 4 is the multi-effect evaporation. 5 is the multi-effect evaporation with vapor compression. 6 is the multi-stage desalination. So for all of them, this equation and this one definitely are going to be always used. These are the starting equations that we start our models with. This equation is coming from the fact that we do a salt balance. So m dot feed into x feed is m dot brine into x brine. I could not say m dot distillate x distillate because basically x distillate is 0. We assume the vapor as pure vapor and it is free from salts. Accordingly, when I'm looking for the energy balance as it enters into the unit here, the quantity which is coming here basically is nothing but m dot m plus m dot entrained vapor. This is the quantity of steam which is entering here at saturation condition Hg, and it will condense to HF. So when I'm looking at the energy input to the unit, to the evaporator, the Q evaporator, this is m dot motive plus m dot entrained vapor. Both of them are mixed together. They are leaving the TVC to enter, and they are going to condense from Hg to HF. So this is the energy in. Last time, when we were considering the single effect evaporation, we used to call this m dot steam, and that steam was coming from the power plant. Now, this steam, part of it is coming from the power plant, and part of it is generated from our own system, which is the entrained vapor. This is equal to the feed that is going to be sensibly heated from T feed to TB. So this is sensible heating of the feed, and this is the formation of the vapor by evaporation. And one more thing here, because we are talking about m dot m and m dot entrained vapor, what is going to relate these components together is the entrainment ratio. Ra is m dot motive divided by m dot entrained vapor. So these are connected by the RA. Still, we have more than one unknown here, which means that this RA, we should have a way to calculate it so that we establish a relation between m dot motive and m dot entrained vapor. Along with this equation, then we can solve them and obtain each component of them alone. So this is the energy balance for the evaporator. Energy balance for the condenser is the same, but remember the change. Here, we are talking about m dot C. It's not m dot D anymore. It is only part of it because we know the m dot vapor that has been generated, which is nothing but the m dot distillate. This now has been splitted into m dot entrained vapor plus m dot C going to the condenser. This is going to go to the ejector, entrained in the ejector, and this is going to the condenser for condensing. This quantity is going to condense from saturated liquid to saturated vapor. So it's basically m dot C into HFGC, which is basically this lambda. In the engineering units, they use lambda for the latent heat of condensation rather than the value HFG that we are used to. And these are in balance with the quantity of seawater, which is going to get into the condenser, which is m dot feed and m dot cooling water, that will be heated sensibly from T cooling water to T feed. So this is basically the balance, the energy balance in the condenser. And for the areas, again, we are going to consider what we talked about last time. For the evaporator, we're going to have T steam constant, and we're going to consider TB. So it's just a temperature difference here. So Q is U evaporator, area of the evaporator into the temperature difference. Once you know the value of U, we have already calculated Q from the previous slide, which is basically the feed being heated to TB and part of it has evaporated. When it comes to the condenser, then we are talking about a condition where the temperature of the vapor is constant, but the feed is going to be heated from T cooling water to T feed. So we need to calculate a log mean temperature difference, which is this. And again, Q condenser is going to be U of the condenser, area of the condenser into the log mean temperature difference in the condenser, and you can get, this is typically similar to what we have done last time. Yeah, the equation that we have here is the equation that's taking care of the entrainment ratio. What we see here is an empirical equation that has given by a researcher, his name is Power, in 1994. He came up with this equation, and this equation have been given as shown here in this in this expression. So RA, which is, again, to remind you, it is nothing but m dot motive steam divided by m dot entrained vapor. This is equal to a constant into PS to the power 1.19 divided by the entrained vapor to the power 1.04 into the motive steam pressure over the entrained vapor pressure, all to the power 0.015 into pressure correction factor divided by temperature correction factor. The pressure correction factor is given as a function of the motive steam pressure. The temperature correction factor is given in terms of the entrained vapor temperature, which is the saturation temperature corresponding to the vapor pressure which is leaving here. Or you can look at it as it's the saturation temperature corresponding to this pressure. And the definition of each one of these terms given here. RA is the entrainment ratio, defined as the mass of the motive steam per mass of the entrained vapor. PM is the pressure of the motive steam. PS is the discharge mixture pressure out, which is leaving the TVC. And PEV is the entrained vapor pressure. What we did after that is that this is basically the model. We have combined all of these components. We put it into the ES to look at the results. And actually, we have here resolved the equation that we took last time, the same model that we took last time, but what we did only is we have added the TVC with a compression ratio of 2.5, as you can see it here. Again, the value of the m dot feed is 2.5. The m dot distillate is 1 kilogram per second, which is this. And we did the analysis, doing the analysis, and we took, yes, the motive steam pressure is 750 kilopascal. The entrained vapor pressure is 37 kilopascal. And the discharge pressure is 92.5 kilopascal. This is the pressure correction factor calculated, and the PR of that unit turns out to be 1.48. When we did the analysis last time, we had a PR of 0.97. Now you can see how much is the increase in the performance ratio just by adding these components. The rest of the data are given here. This is the value of the entrainment ratio, 1.818. The specific heat transfer area is smaller because we are using a smaller condenser now. And this is the temperature correction factor. And these are typically the temperatures that are given to operate the unit. So we can see that, yes.
The work of the compressor is not included in these equations.
There's no work. This is not a mechanical compressor. This is a thermocompressor. A thermovapor compressor, it does not have moving parts. It is basically something which is looking like this.
Okay.
And as a matter of fact, no, this opening is somewhere here where you are entraining. This is basically the motive steam. It is entraining the vapor here. They are mixed together here and they are increasing the pressure increase here is due to this part of diffuser, which is there. So it's not a compression due to a motion of a shaft, but it is a compression due to going through an increased area, the velocity reduces and the pressure keeps increasing somehow here. So it is not a mechanical vapor compressor, it's a thermal vapor compressor. Let's consider here, maybe we can look at this in terms of an example, just so that we can go together through the process of the calculations, or at least not even to the numbers, but at least putting things together. So we're talking about a single effect evaporation system with thermal vapor compression. And the data that we have brine saturation temperature of 70 degrees centigrade, feed salinity of 65,000 ppm. We have, sorry, this is not a feed salinity. This is the rejected brine salinity. This is XB. XF, the feed salinity is 45,000 ppm. We have the cooling water is coming at 25 degrees centigrade. And we have the boiling point elevation, 0.82 centigrade. The overall heat transfer coefficient in the evaporator and the condenser are basically 2.48, 1.95 kilowatt per meter square Kelvin. The CP of the seawater is 3.88 kilojoule per kilogram Kelvin. The compression ratio is 2.5. The motive steam pressure is 750 kilopascal, and the entrained vapor pressure is 37 kilopascal. And yes, HFG of the vapor is 2355 kilojoule per kilogram. Did I miss anything here? Yes, it is even providing us here with, it could have provided us with one of two things. One way, for example, we say that we are going to do that for an m dot distillate of 1 kilogram per second. So we're going to operate it per unit mass flow rate. Or I can come here and say, no, this is not exactly what I'm going to do. But instead of providing with m dot distillate, we can provide a feed flow rate. And this is decided to be 25 kilogram per second. And then what we need to do is to go through the analysis of the unit and get the missing things. What are the missing things? What we need to calculate is going to be m dot motive, Q in the evaporator, Q in the condenser, area of the evaporator, area of the condenser, PR, and definitely we need to know how much is the m dot distillate, how much distillate that we are going to get from this unit. Let's look at the main elements that we would need to see in the solution here of this problem. We're going to start as usual. M dot feed is equal to m dot distillate plus m dot rejected brine. We don't know the distillate, but we know the feed. It's 25 kilogram per second. And m dot feed, x feed is equal to m dot brine, x brine. We know m dot feed, we know x brine, and we know x feed. So from here, we can get the value of m dot brine. We substitute back here to get the value of m dot distillate. So this is, to begin with, this is the mass balance that we need for this system. One second thing we may consider is that the TV is basically temperature of B minus boiling point elevation. So this value can be calculated. TB is already given here. It is given as 70 degrees centigrade. So the value of TV can be obtained. Then PS, we said the compression ratio is 2.5. So PS is 2.5 into P entrained vapor. We have the P entrained vapor. So from here we can calculate PS and you'll find it as 92.5 kilopascal. TS is the saturation temperature of PS. You can get that from any thermodynamic calculator. You can get it from the ES, and you can find here that the value of TS is to be calculated as 97.44 degrees centigrade. Why do we need this temperature? Because we can calculate HFGS at this temperature, and the value is 2263 kilojoule per kilogram. Then we have the equation of the entrainment ratio, the empirical equation that we have, which is a function of both pressure correction factor and temperature correction factor. And these two values are going to be calculated. So the pressure correction factor is 1.104. Temperature correction factor is going to be 0.96, from which the RA is going to be calculated as 1.813. This is nothing but m dot motive over m dot entrained vapor. We needed this relation between motive and entrained vapor because QE, which is Q in the evaporator, is going to be m dot feed. We know m dot feed, CP given to us, TB given minus TF given, plus m dot vapor or m dot distillate. We have already calculated it here into HFG vapor. So from here, the value of Q is known to us. We know how much is it. This Q also is equal to m dot motive plus m dot entrained vapor into HFGS. HFGS, here is it. We obtained it here. And we have obtained the relation between m dot motive and m dot m here. So from here, we can calculate m dot motive and m dot entrained vapor. Once we know that, since we are here, we have m dot m, which is the first requirement here in this problem. And not only that, but we can even at this state calculate PR. So PR is m dot distillate divided by m dot motive. This is the external steam. And this value can be calculated. Then we can move forward, and now we know the value of QE, we know the value of M dot M, we know the value of PR, so are left with QC. QC, and this is, by the way, one of the common mistakes normally you fill in while you are solving problems like that. Because we say that QE is equal to M dot distillate into HFG of the vapor. Typically we do that, but this is not true. Why not true? Who can tell me why?
Due to entrained vapors, because they have moved to the TVC.
Exactly, because some of the vapor has left to the TVC. So what's going on here is not going to be M dot distillate, it's M dot C. And the M dot C here is nothing but M dot distillate or M dot vapor minus M dot entrained vapor. This is the mass flow rate which is going to go to the condenser, and we can calculate it. So QC can be obtained here. And accordingly, we can calculate the area, but for the area, we need the log mean temperature difference. So we'll just make a quick sketch here. This is the temperature of entrained vapor, or temperature of the vapor in general. And this is basically T cooling water, and here TF. This is delta T1, this is delta T2, so I can calculate the log mean temperature difference. QC is nothing but overall heat transfer coefficient into the area into the log mean temperature difference, and from here we can calculate the area of the condenser. Then what is left is the only area of the evaporator that needs to be calculated, which is something that we can do here. Again, simply Q evaporator is the overall heat transfer coefficient in the evaporator into the area of the evaporator into the temperature difference Ts minus Tb. This is known, this is known, this is known. So from here, we calculate area of the evaporator. We may also, this is all that we need here. This is what has been needed in this example, but we can take it one more step further by saying that in the condenser, we have already calculated Q condenser, and that Q condenser is, well, calculated that before here as M dot condensate into HFG of the vapor. This is also is equal to M dot feed plus M dot cooling water into Cp Tf minus T cooling water. And then we can calculate M dot cooling water from here. At the end, the specific mass flow rate of the cooling water is mass flow rate of the cooling water per mass flow rate of the distillate, and specific heat transfer area is the area of the condenser plus area of the evaporator divided by M dot distillate. And we have already before calculated the value of PR. So these are the kind of performance parameters that we need for such a system. What is new here? What has been added? Only the part which is related to the performance of the TVC. It has been considered here. It has been added to the energy equation of the evaporator, and that's the only difference. Otherwise, analysis is very much the same to what we have done last time with single effect evaporation. The expression that we have and that I've shown you in the analysis where we calculate the value of the entrainment ratio, a constant into PS to the power 1.1 something divided by the PEV to the power 1.04 into the temperature ratio into the pressure and correction factors. This is the equation that has been, as I mentioned, it has been proposed by Power. This is not the only equation which is available for ejectors. You can find another equation which is in the form of a polynomial, and you can use either one to come up with the expression that you would have for the entrainment ratio and then calculate the flow rates. So it's not a single equation, but there is that equation. There's another equation that has been given, I might be able to share this equation with you once in some of the work that we have done lately, and we accounted for this equation to calculate the entrainment ratio. But power equation is a very well-known equation, and many are using it for the analysis. Any questions? Okay, in case no questions, we can further go ahead and move into another kind of compression, which is associated with single effect evaporation, which is the case in which mechanical vapor compression. So for this one, I'm going to share this file here, talking about a single effect mechanical vapor compression system. The symbols that can be used is single effect evaporation with mechanical vapor compression. So this is the system that we will be looking at now. The difference here is that it's not a thermal compressor, but it is a mechanical compressor here. And there's something here unique about this because of the word mechanical, that we do not need a boiler. We are going to be talking about a desalination system, which is run by a compressor, and the compressor needs shaft work. The shaft work can be provided by a diesel engine. So you are talking about a unit here, which is a standalone unit. You do not have to link it to a power plant. You do not need a boiler. All what you need is take it as it is, put it anywhere, and deliver seawater or whatever quality of water into it, and then it will produce. So we're talking about a compact standalone unit that would operate. And this is an additional benefit that has liberated the thermal desalination systems from having to be sticking into a power plant or being part of an integrated power plant desalination unit. That this one does not need that. And it's not only that, but lately you may think of, well, you don't need a diesel engine. Why don't you take this and take the power from PV panels so that the unit can be operated based on renewable energy, and it would work fine then. The only problem or the only drawback associated with this type of desalination systems is that so far the power requirements are in the high side, and you need substantial amount of power to operate. If you find a way to reduce the power, then you are going to have a real competitor performance for this. We have done some work with it. Even we had a patent that has been filed in that has been published actually in 2019, which is considering one way to do sort of thermodynamic balancing to reduce the total amount of power needed to operate such systems. I'll be talking about that a little bit later when we get to the MED system. So it's an attractive system among various single-stage desalination systems. Why? Because it is compact, it is confined, it does not require external heating source. It's not like the thermal TVC, which needs steam from a power plant. It's not like the absorption, where you need like a whole absorption system to be there, be it using lithium bromide or lithium chloride or calcium chloride, and having an absorber and a regenerator. It's not like the adsorption units where you need a desorber and absorber. You don't need that. All you need is a way to run a compressor to compress the vapor. That's all. The major components of this system include a mechanical vapor compressor, an evaporator, a couple of heat exchangers, pumps, and venting system to get rid of the non-condensable gases. One other feature which is interesting in this system is that when you read here from part 1 to part 5, there's no condenser. And that's true. We do not need a condenser for this unit. But we need a couple of heat exchangers. Are they mandatory? Do I have to use the heat exchanger? Not really, but this is just for energy recovery. That's all. So these are there to enhance the performance of the system. This is the system layout. And what you see here on the right-hand side is a couple of heat exchangers, sensible heat exchangers. And the heat exchangers here are only for one reason, which is to increase the temperature of the cooling water from T cooling water to TF. This is all. But here, there is liquid entering here, and there is liquid entering here, and this is seawater being splitted here. So there's no vapor to condense. So there's no condenser here. Let's follow that. What's going on here? What's happening? Basically, seawater is taken from the sea, and it's only seawater, it's only feed. There's no M dot cooling water here, there's no need. We used to have M dot cooling water whenever we had steam, and we need to make sure that all the steam will condense. We don't have steam here, so we're only going to have a certain M dot feed. That's all. Even the M dot feed is going to be splitted. Part of it will go here, and part will go here, where it will be heated from T cooling water up to T feed. The feed here is being chemically treated, deaerated, and it will be sprayed in the evaporator, the regular way that we have seen. And it will be sprayed over tubes that have steam inside. So what will happen? A thin film of the seawater will form on the outer surface of the tubes, where it will be heated to TB, the saturation temperature, and part of it will evaporate. The rest that will not evaporate is going to be fall down, and it will be rejected as rejected brine at saturation temperature. And because here it is at saturation temperature, the high temperature, you don't have to throw it away to the sea right away. But what you do is the part which is being, before you throw it away, you pass it by a heat exchanger so that you can preheat the seawater. That's all. So instead of introducing the seawater at low temperature here, and you have rejected energy, we make use of the rejected energy to preheat the part of the seawater. So this is for the brine. The part of the vapor that was going to evaporate, it will pass by the mist eliminator so that we can get rid of the of the droplets that would be entrained, and the vapor, all of it, is going to be taken as input to a mechanical compressor. The compressor is going to compress the vapor from saturated liquid to superheated condition. So from the suction side of the compressor to the delivery side, where we have basically high pressure or higher pressure and higher temperature. Then this remember that superheated vapor here is all of it our product. This is the vapor that has left here. You are collected all the vapor, you enter the vapor into a compressor, you compressed it to high pressure and temperature, and then into superheated steam. Steam is entering here, where it will condense in the tubes of the evaporator into product water, sweet water, but sweet water at high temperature. Before taking it to our sweet water tank, we pass it by a heat exchanger so that we can heat the remainder of the seawater needed to the temperature TF. So the seawater which is coming before we enter it to the system, part of it will go to the brine preheater, part will go to the distillate preheater to preheat it from T cooling water to TF. And then the brine was going to be rejected to the sea, and the seawater will be taken into the seawater or desalinated water tank. And the system remains as this kind of component. There is an evaporator and compressor. Vapor will form, it will be compressed to high pressure and temperature, and will condensate inside the tubes here, and this is basically our product. So again, the idea here looks beautiful, because it's a simple idea, it's a compact layout. The only problem that we have so far is that the power requirement to run this system are considerably higher, and we need to have a look at this to see how can we reduce that. Don't forget there is a vent here so that we can get rid of the non-condensable gases. So any carbon dioxide or something that is going to be coming or operating or showing here due to the evaporation of the seawater, that's something that we can get rid of. So whatever will go to the compressor should be only pure vapor coming in. The compressor and the evaporator are usually made of one unit. And I have to tell you that I might be showing you a figure now where these two heat exchangers are even compacted in a single heat exchanger, but has two fluids. The seawater is passing over tubes of tubes of seawater or tubes of sweet water, and thus the heat exchange is occurring between them. It could be even a plate heat exchanger. The evaporator is the same as we have seen in the TVC, and we have same as we have seen in the regular single effect evaporation system. These are some special requirements for the operation of the unit. The temperature difference between the steam and the distillate would be between 4 to 10 degrees centigrade, which is the degree of superheat in the compressor. The difference between the feed to the saturation condition is 1 to 5 degrees centigrade, and we have done that in the previous couple of systems where it was 5. Remember, the T feed was 70 and the T saturation was 75. So a temperature difference of 5 for sensible heating only. The difference between TD distillate and TB, again, somewhere in between 1 to 5 degrees centigrade. And the difference between T0 and the T cooling water. The T0 is the temperature of the seawater. It will cool down from TD to T0, and this is going to cool down from TB to, we said, let it be also T0. So this is the rejected fluid temperature from the two heat exchangers, so that we can just keep the heat exchanger size small. It's recommended to have the temperature difference as 1 to 5 for the fluid that will be cooled in the heat exchanger. Maintaining these temperature differences is going to keep the compressor power in an acceptable range. We're going to have even the evaporator heat transfer area will not be too large for this. And we are going to have like a moderate values for the overall heat transfer for the log mean temperature difference values that will be needed in the 3 heat exchangers that we have here, or the 2 heat exchangers and the evaporator. Material balance, as usual, we are going to have an evaporator. In this evaporator, there is m dot feed coming in. And it is going to be splitted into m dot vapor leaving at the top and rejected brine leaving at the bottom, as usual. So m dot feed is m dot distillate plus m dot brine. M dot feed x feed is m dot brine x brine. So these two equations are enough to calculate m dot feed and m dot brine, provided at the salinity of the feed, the brine, and the distillate quantity are given. So there are basically 2 equations and 5 unknowns, or in 5 variables. 3 of them should be known so that it becomes 2 equations and 2 unknowns, and you get these values in. And then we have a couple of heat exchangers. There's one heat exchanger where part of the seawater comes in, and there is another one where the rest of the seawater comes in. This basically is m dot feed. Part of it will go here, and this m dot feed has a temperature of T cooling water, and these 2 streams are going to leave here and combine together as m dot feed at a temperature T feed. So if you consider these two units together as a control volume, then you can say that Q of both heaters is equal m dot feed, which is this quantity, Cp of the feed, T feed minus T cooling water. So here this is balance for the two heaters together as a control volume. You need to look at each one of them separately, fine. Then what we do is we take one of them. For example, this is, let's say this is the distillate. So m dot distillate is entering at T distillate and leaving at T node. And this is a fraction of m dot feed. Let's call it alpha into m dot feed. So the balance here becomes Q of the distillate preheater is equal to m dot distillate Cp T distillate minus T0. And this is equal to alpha into m dot feed, fraction of m dot feed, which is coming here, Cp Tf minus T cooling water. The same thing applies here. Here we have brine entering, m dot brine at T brine, and it will be cooled down to T naught. Should it necessarily cool down to T naught like this? No, this is just for mathematical simplicity. We say, let's do it this way. So Q for the brine preheater is m dot brine Cp T brine minus T naught. This one is in balance with 1 minus alpha of the feed, T feed minus T cooling water. So here you see the analysis of the two heat exchangers together and the analysis of each one of these heat exchangers alone. Definitely, each one of these heat exchangers can be said that Q distillate preheater is overall heat transfer coefficient of this into the area of it into the log mean temperature difference. And Q brine preheater is also U brine, A brine into the log mean temperature difference for the brine. This is for the distillate, this is for the brine. So that the picture for the heat exchangers becomes complete. I'm going to talk about this balance equations again, but it is just now because we talked about the balance equations of the two exchangers together. I thought let's look at this in contrast with writing the balance equation for each one of these heat exchangers alone. The first part on the top here, you don't have to pay much attention to. Here he's looking at Q for the two heat exchangers together. We have seen this expression. This is the energy given by the distillate flow rate. This is the energy given by the brine flow rate. Each one is in its own heat exchanger. Why he's doing this here? Because he's looking forward to get a closed form expression for the T node. Do we have to do that? No. And again, I don't like to have sort of a closed form solutions where we have to memorize this equation. There's no point of doing that. Let's do the analysis one by one, and then we'll get everything detailed in terms of the answers that we are getting for the expressions. So we have seen now, coming to the evaporator. The evaporator, a couple of things are occurring there. We have superheated vapor here, which is entering, which is leaving the compressor. So we have basically m dot distillate, which is going to enter here into these tubes, where it is superheated. Why superheated? Because we don't want condensation to start occurring outside. So you give a little degree of superheat for the vapor, which is leaving the compressor, so that the condensation does not occur. You make sure that what will enter here is going to be slightly superheated, so you you are going to make sure of all, or make use of all of the latent heat which is going to form here. So you are going to enter here as sort of superheated vapor. So there is a degree of desuperheat. There is a reduction in the temperature of the superheat here. So QE, when you look at it from, sorry, it's just this thing happened. I'm going to load it again so that we look at this expression. Yeah, we were here. We're talking about the distillate as it enters into the evaporator. It enters slightly superheated, and then its energy is going to be as follows. I'm talking about the evaporator and steam which is coming here as superheated. First, it will be desuperheating. So it's going to cool down sensibly so that a sensible cooling of the vapor is going to occur here, which is taken care of by this expression, m dot distillate, Cp of the vapor, it's coming as a vapor, Ts, and it will cool down to a temperature Td. Remember, it will enter here as Ts, it will cool down to Td, after which it is going to condense, and then it will leave as liquid. It will leave as liquid at a temperature Td. Td is the saturation temperature. Ts is a slight superheat. So first, a desuperheating is occurring here. After that, condensation is going to occur. So it will first reduce in temperature to the saturation condition, after which it's going to condense, given off the latent heat, to the sprayed seawater, and then leaving at a temperature Td. So this equation is the equation of the energy given by the superheated vapor which leaves the compressor. And then what would it do? We have feed coming in here. This feed is going to be heated sensibly to Tb, and then part of it is going to evaporate. So this equation is typical to what we have seen earlier. We have feed coming to be heated from T feed to Tb, and a part of it is going to evaporate as we see in this part. So this is the energy balance within within the evaporator. So how does it look like? It simply looks like this. The steam side is going like that. This is a straight line, and this is a degree of the superheat. So this is m dot distillate. And what you see here is that the feed is coming with a slightly small temperature, and then it increases here. So this is T feed, and this is TB. And now you may remember the kind of temperature ranges that were given further, looking at what would be typical temperature difference between T feed and TB, what's typical temperature difference between TS and TD, and what's the typical temperature difference between TD and TB, so that you can keep the sizes in an acceptable range. And that tells something. Whenever we are looking for areas that are needed for the unit, then will it be a good approximation to neglect the desuperheating or the subcooling or sensible heating here and consider only the part of constant temperature, or we have to account for these? That's a thing that we need to look at. These are additional equations, simplifications and simplifications and simplifications. I don't prefer doing that because you don't need them while you are analyzing a system or solving a problem. The basic equations of the energy balance are the ones that we rely on. And what we see here in front of us is that I assumed that the desuperheating is too small to be considered. The sensible heating is too small to be considered, and the substantial amount of energy here is spent in constant temperature heat transfer part. So when we calculated the area of the evaporator, you can see here, U, overall heat transfer coefficient in the evaporator, into area of the evaporator, TD minus TB. Overall heat transfer coefficient, area, TD minus TB. Both of them should be the same, by the way, or approximately the same. They'll never be the same because of that issue of temperature differences and how much of the sensible part that you are neglecting. But anyway, this is a first hand approximation that you are going to say, I'm going to neglect the effect of sensible heating or heat transfer associated with sensible heating. Is it a big deal? Not really. I mean, you can just calculate a log mean temperature difference for this part and add it. That will be more accurate, and it's not a big additional work to be done. And the same thing is here. Maybe I can put like an exercise in the next homework where you can do this. You can just see what if we include this and include that. It's going to be tedious in terms of analysis? No. It's going to affect the results? Yeah, yes, it would. And that would be interesting to look at. And this is how to calculate the log mean temperature difference in the feed preheaters, which basically the distillate preheater and the brine preheater. The only equation which is left for us that I will close with is this equation here, which is the equation that calculates the mechanical power needed for the compressor. We copied this equation from what we have studied before in thermodynamic courses. When we're studying a vapor compressor unit, then the work of the compressor is being given here. Gamma is basically the ratio between Cp and Cv for steam. And then this is the suction pressure and volume. Eta here is the efficiency of the compressor. Gamma, again, we said it's Cp over Cv. PS is the delivery pressure, PV is the suction pressure, and gamma is there again. So this is a typical expression that we use for calculating the power. And the power here, the performance of the unit, we can calculate a specific heat transfer area. There's no specific mass rate of the cooling water because we are not using additional cooling water for this unit. But we have SA. We don't have a PR because we don't have steam, which is coming from a power plant. But instead, we have what we call specific power consumption. So the analysis of units that are operating with mechanically, like the PO, like this one, like the mechanical vapor compression, like the RO, like the FO, these units are all estimated the power in terms of specific power consumption. We are going to start our next class probably with an example so that we can go through that detailed calculations of this type of units. Oh, that would be it for today, and we'll see you inshallah on Monday. Just a little reminder that only 2 groups have submitted a progress report for the project. I'm waiting for the rest to arrive today, inshallah, sometime.